This is a video for AQA Further Pure Mathematics, Sequences and Series, section 3.1, where we're introducing the idea of polynomial approximations and Maclaurin series. Well, by a polynomial approximation we mean taking any function and writing it as a polynomial of the form a plus bx plus cx squared, etc., where a, b and c are real numbers. Now if the coefficients a, b and c are chosen correctly, this polynomial will get closer and closer to the function as the powers of x increase. The reason for doing this is that polynomials are easier in general to manipulate than some complex functions. So it gives us an easy way of being able to evaluate complex functions or to, for example, differentiate, etc. These polynomial approximations are known as Maclaurin series. So we're going to look at a Maclaurin series for one particular function now. That's the function sine x. This is the approximation power 1, and you can see that what we've got is p of x, the polynomial, is equal to x. It's not particularly good approximation, you might say, although it does go through the origins, as sine x does, and at that point it does have the correct gradient. Now what I want to do now is to use a GeoGebra file which will show what happens as we increase the value of n, so we're looking at different powers of x. Well, this is the GeoGebra file now, and you can see that we've got our polynomial there equal to x when we've got power 1. We can increase the power to 2, and you see nothing actually happens. There is no approximation involving x squared for sine x. But if we move up to 3, then you can see there's our second approximation, which has got x cubed in it. So we get x minus x cubed over 3 factorial. And you can already see now that it's beginning to look more like the sine curve, at least close to the origin. There's no power 4, but if we put in power 5, you can see what's happened. And keep going now. And you can see that it's the odd powers which add in to this polynomial. The sign is changing each time from positive to negative, so we've got minus x cubed over 3 plus x to the power 5 over 5 minus x to the power 7 over 7. And already we're very close to a function which is correct for one complete cycle of sine. Now we can keep going with this, seeing that as we increase the power, the polynomial gets closer and closer, and by the time we get to power 17 we've got a function there which is a very good approximation over the range from negative 2 pi to 2 pi. So increasing the power of x and looking at the polynomial gives us closer and closer approximations. So we've seen there how the approximation gets better and better as we increase the powers of x. And this is just the first few of them, up to x to the power 5, and then the next one x to the power 7. Now in general then, the formula, you could see that we've got x to the power, it's the odd powers, and each time we're dividing by the factorial of the power, and the sign is changing. So in general we can write that as follows: sine x is equal to x minus x cubed over 3 factorial, then it's plus x to the power 5 over 5 factorial. The next one would be minus 7 x to the power 7 over 7 factorial. As a general expression, then the negative 1 to the power r, that's the part of the expression which changes the power, it changes the sign from positive to negative each time. The power is an odd number only, so we've got 2r plus 1. 2r plus 1 is always going to give you an odd number. So if you put r equal to 1, that will give you 3. So 2 times 1 plus 1 is 3. R equal to 0 will give you the power 1, and so on. And the 2r plus 1 on the bottom line factorial, that gives you the factorial changing. So that's its general expression. Now, for example, we could use that then to give an approximation for sine pi by 3, and simply by substituting the value pi by 3 into the expression. If you put that into your calculator, you will find that your calculator gives you a value of 0.866 and then 295 2838. You might like to compare that with the value of sine pi by 3 given by a calculator. The calculator gives sine pi by 3 as being equal to 0.866 and then 0.254. So you can see this approximation is actually correct up to the first 3 decimal places. It's a little bit larger than the correct value of sine pi by 3, but that's to be expected if you think about the next term, which is going to be minus pi by 3 to the power 7 divided by 7 factorial, so that would subtract a little bit from this. Well, that's the end of this video looking at an introduction to Maclaurin series. In the next video we will look at other functions and see how we can then use them to approximate more complex functions as well.